Hi, Mr. Cowan.
How are you doing tonight?
I'm all right. How about yourself?
Good. So what are we working on tonight? What do we got?
So I have a test on Friday.
Okay.
So I was just going to go through the textbook and pick out any review problems that look a little confusing.
Okay.
So I did notice these ones. It's just two problems, and it says the directions are use the change of base formula to evaluate each logarithm. And the first one is log base 4 of 19.
Okay. Let's talk about this. Log base b of a. Change of base formula says this. Okay. The way I kind of remember it, it's the log of the bigger. By bigger, I mean larger in size, not in numerical quantity, divided by the log of the smaller. In other words, if you had log base 2 of 3, that would be the log of 3 divided by the log of 2.
And that would
Would
be common
also
log?
be, and it could be any of these. These are all the same ratios.
Right.
In other words, the base does not matter. As long as the log of 3 over the log of 2, that's the change of base rule. So what was your problem? The log of what?
Log base 4 of 19.
So what's that going to be?
Log, just common log of 19 divided by common log of 4. Or I guess I should use natural log, right?
No, either one. I've grown accustomed to natural log because once you get to calculus, everything's kind of a natural log. So I tend to recommend to pre-calculus students that are going to take calculus that they switch to natural log as soon as possible almost.
Okay.
In other words, that's the same ratio as this. Okay, what else you got?
So that takes care of that one. Okay, yeah, so these are graphing problems.
Okay,
And it says graph each function, determine the domain, range, and any asymptotes.
okay.
So f of x equals 2 to the power of x minus 3.
All right, let's talk about domain. What's the domain going to be? Remember how to think about domain.
Right, what can x not be?
Thing that x cannot be. In other words, you start off domain being all real numbers, minus infinity to plus infinity.
Right.
And then you start restricting it based on the context. If I have 1 over x, well, it can't be 0. If I have the square root of x, well, it's got to be greater than or equal to 0. If I have the log of x, it's got to be greater than 0. So you kind of look at domain as what can x not be? Is there anything x cannot be?
I don't think so.
So the domain is all real. And you can state that in a number of ways. You want to put it in interval notation, it's minus infinity to infinity.
Right.
About the range. Range is always harder than the domain. Figure out. Now, it can be helpful sometimes to graph it. what would y equal 2 to the x look like as a graph?
But yeah, like that.
They all look like that, regardless of what the base is. From this graph, I can tell the domain is negative infinity to positive infinity, right?
Yes.
What's the range? Of this function right here, and that graph that I've drawn.
0 to, yeah, it's 0 to infinity.
And is it a parentheses or a bracket around the 0?
Parentheses.
Because it can never be 0.
Right.
There is no value of x that you can possibly come up with that would make y 0. It approaches 0 as x goes towards negative infinity, but it never actually hits it.
Right.
So therefore the range is 0 to infinity, which you can read off this graph, and it's 0 with a parenthesis. Now, what's the difference between your function and my function? What is 2 to the x minus 3 power? How is that different than 2 to the x?
It's a horizontal shift to the right, 3 units.
Okay, so all I'm going to do is take that point right there, shift it 3 units to the right, and draw my graph through that. Now, it doesn't affect the domain. The domain's still all reals. What happens to the range?
Nothing.
Exactly. Horizontal shifts do nothing to the range, ever.
Right.
Vertical shifts, if I put a minus 4 in there, well, now that moves everything down 4 units, and my range would be minus 4 to infinity, because it would look like that.
Right, and the asymptote would be x equals negative 4. Or, sorry, y equals negative 4?
Yes. The asymptote in the function you gave me is what?
Just y equals 0.
Okay, and it's a horizontal asymptote.
Right.
Okay. Yes. Yeah, if I put a negative 4 in there, then it would move that horizontal asymptote down by 4 units. What else did they want? Domain, range, and asymptotes, that's it?
Yeah.
Okay. There's no vertical asymptote here.
I was just about to ask.
Yeah, it's not that obvious from looking at it. Even if we look at my function, y equal 2 to the x, one could imagine that maybe there's a vertical asymptote like that, but there isn't. If you look at y equal 2 to the x, as x gets bigger, y gets bigger, always. You make x 100, y is a big number. If you make x 1,000, y is an even bigger number. In other words, you can keep increasing x and y will keep getting bigger. But there's no vertical asymptote. There's nothing that would prevent x from being this value that I've drawn the black line on. So it might look like there's a vertical asymptote there, but if you look at the function, you know there isn't. Vertical asymptotes come from things that look like this.
Right.
In other words, x cannot be 3. Therefore, that creates a vertical asymptote at 3. X, you can also, this also gives you a horizontal asymptote at 1. And your function is going to be hyperbolic in nature and look something like that. So that's the kind of thing that creates vertical asymptotes, is whenever you're trying to divide by 0.
Okay.
But not so much a function like what you gave. In fact, I can almost say that the only thing that creates vertical asymptotes is, no, not quite, division by zero. If I said this, that has a vertical asymptote in it.
Right.
Looks like that. And the vertical asymptote is x equals 0. Because x can never be 0. You cannot take the log of 0. So it kind of, vertical asymptotes tend to boil down to if x can't be 0, or if the argument can't be 0, then that creates a vertical asymptote.
Okay. The argument being x with any
Now,
horizontal
let's say if
information.
I had this, the log of x minus 1. Well, now, x minus 1 has to be greater than 0, which means x has to be greater than 1, which means you're going to have a vertical asymptote at 1. And the function is going to look like that. So that's what I mean is when the argument is equal to 0, that also creates vertical asymptote. Not just division by 0, but it's also taking logs of 0.
Okay.
You haven't gotten to trig yet?
No, not yet. I think that's just next semester.
Well, yeah. I have a pre-calc student that's on the same schedule you are, pre-calc this semester, trig next semester, and he hit me up with trig tonight.
Really?
Yeah. So I was wondering if the same thing maybe is not true with you, is that they're starting trig a little early, but
No, I don't think I've gotten anything.
no, I think this student goes to, let's see, you go to Rock Canyon, right?
Ralston Valley.
Alston Valley. I think this student goes to Rock Canyon. Okay.
Okay.
What else?
So, the directions for these, it says solve each equation and then verify your result using a graphing utility.
Okay.
And then it's, oh, I'm sorry. Log base 3 of the square root of x minus 2 equal to 2.
Okay. So the way we want to solve this is how? In other words, when you have an exponential equation, you use logs to solve it.
Right.
When you have a log equation, how do you solve
You make it exponential.
it? Okay. What's the exponential expression of this?
3 squared equals the square root of x minus 2.
Now we have an algebraic equation that we can easily solve. What's the next step?
Square both sides.
That gives you 81 equals x minus 9. So x equals 90, right?
Wait, where did you get x minus 9?
When I squared both sides, 9 squared is 81. This squared is x minus 9. Whenever you square the square root of x, you get x.
Right. In the original equation, it was x minus 2.
What did I do wrong? Excuse me. Sorry. So it's 3 squared equals x minus 2, the square root of that. Square both sides. And you get this. And finally, x is equal to 83. Now, let's plug it into the original equation. Do we violate any domains?
No.
Okay. Now, how would you prove that this is okay by graphing it? How would you prove that the solution is x equal 83?
Put it into the calculator and then put in the equation x equals 83.
Here's the way I would do it. Y sub 1 equals the log base 3 of the square root of x minus 2, and y sub 2 equals 2.
Oh, right.
Okay, what you're going to get is something that looks like this, and that right there is going to be at 83. In other words, the left side of the equation goes in as one function, the right side of the equation goes in as another function, and where they intersect gives you the solution for x. Not y, but x.
Okay.
And if you graph these two like this and find their intersection, it'll be where x equals 83. You have an inspire, right?
Yeah.
You know how to graph two different functions?
Yeah.
Okay. And then find their intersection. It's actually easier on an inspire than it is on a TI-84. Okay.
Not much. I got 11.
For x?
Yeah. Maybe I put the equation wrong. Oh, yeah. I forgot to put the square root.
Okay, that would make a difference, because if I didn't have the square root sign there, then I would have 9 equals x minus 2, and that would give you 11.
Yeah.
So, but the square root changes everything.
Yeah, 83.
Okay, cool. And I think that's how they want you to do it when they say verify in your graphing calculator.
Yeah.
I think they want you to make two different functions and find their intersection. Okay?
Okay.
Just going backwards 1 second. What is the y value when x equals 83?
Two.
Well, I wanted to make sure you knew that. Go ahead.
All right. So same directions. 25 to the power of 2x equals 5 raised to the power of x squared minus 12.
Now, this is a little bit of a different problem. This is an exponential equation, which means we could take the log of both sides and solve it. But there's actually, this is one of those exponential equations where there's actually a simpler solution if you see it. what do 5 and 25 have in common?
5 is a multiple of 25.
5 is an exponential base of 25. Meaning I can express 25 as 5 to some power. That would be 5 squared.
Oh, okay.
In other words, that's the way I'm going to write 25, okay? That's why I put parentheses around it. The parentheses are needed. And that's equal to 5 to the x squared minus 12. Now, applying the rules of exponents, what's that equal to?
5 to the power of 4x.
Now what can I do? Now I got the same base on both sides.
You can set the stuff in the exponential line equal to each other.
Yeah, the exponents have to be equal. Now solve that. How do you solve this quadratic?
You subtract 4x from both sides.
And what?
And then you factor to get x minus 6 times x plus 2.
So my two solutions according to this are going to be what?
X equals 6 and negative 2.
Okay, now because we started with an exponential, we definitely need to check these two solutions.
Right.
In the original equation. So let's check let's check 6. Is 25 to the 12th power going to be equal to 5 to the 24th power? Does that sound reasonable?
Yeah.
Okay, now let's check the other solution. Minus 2. That would mean that 25 to the minus 4 power would have to equal 5 to the minus 8 power. That's also accurate.
But wouldn't it... How did you get negative 8?
Because minus 2 squared is 4. 4 minus 12 is negative 8.
Sorry, I plugged in negative 4 as the solution.
Well, most of the time, when you end up having to solve a quadratic to come up with your two solutions, and you're talking about a logarithmic equation and sometimes an exponential equation, one of those solutions is not going to work. It'll be extraneous. And in all honesty, I thought that the minus 2 wasn't going to work. Because I figured one of them wasn't going to work, and usually it's the negative one. But in this case, it appears to work, because 25 to the minus 4 could be written this way. 5 squared to the minus 4. And then I got 5 to the minus 8. It's definitely equal to 5 to the minus 8. So the minus 2 works, and the 6 works.
Okay.
Now, in terms of proving it on your graphing calculator, graph that with y sub 1, and graph that with y sub 2, and they should cross in two different places. In other words, they will intersect at when x is equal to 6 and when x is equal to minus 2. Want to do that real quick just to verify that they at least intersect in two different places? I'm trying to figure out how that's going to work, but because your graph's going to look, the left side of the graph is going to just look like this. And the right side of the graph maybe is going to look something like this. I don't know. So do you have two intersection points? Probably, yeah. I'm not sure what that graph looks like, where you take a number and raise it to x squared minus 12. But I suspect that it looks something like I've drawn, such that you would have two intersections. You want to do it on your calculator, or you want me to do it on Wolfram Alpha? It's probably worth us checking.
No, I've got it on my calculator, but it's a little wonky. So it's similar to what you drew, but they're much more rigid. Especially the.
Are there 2 points of intersection is the key.
It doesn't. I can't tell. It looks like the graph on the right, so to speak. It looks like it touches the x-axis for.
Well, it might touch the x-axis. The question is, do the two graphs intersect twice? Because we came up with two answers, and they both appear to be valid. Minus 2 seems to work, and 6 seems to work. So
Okay.
the graph definitely should show two intersection points. I may not have drawn it exactly right, but somehow you have to get two intersection points from these two graphs. Now, I'm not sure what 5 to the x squared minus 12 looks like. You know what it might look like? I bet it looks like this. Not what I drew, but it looks exactly like this. I know that that's what 25 to the 2x is going to look like. Well, 5 to the x squared minus 12 is going to look something like this. And you've got two intersection points right there. Only they're going to come at minus 2 and 6 instead of where I drew it.
Right. Yeah, it's negative 2 and 6. So I had to.
It's really going to, I can draw it more accurately than that. I can, sometimes I hate this program.
It's a little glitchy.
The original function looks like that, and the new function is going to cross at minus 2 and then go up very quick like that, so that you have an intersection point there and an intersection point there.
Okay.
Should look like that on your graphing calculator.
Yeah, the 5 to the x squared minus 12 is sort of a parabola with a flat bottom.
Yeah.
And then the 25 to the 2x, it's similar to what you drew it, but it's really, really steep.
Right, but all exponential functions basically look the same. In other words, if I drew this, you would not be able to tell me whether that is that y equals 25 to the x power, or is that y equal 2 to the x power? It's hard to tell because both of them go through that same point of 0, 1. Notice that when either of these, when x is 0, y is 1. So it's difficult to look at an exponential curve and figure out what the base is. Okay, so I know that y equal 25 to the 2x power has to look pretty similar to this. You're right, it's going to go up a little bit steeper. So maybe it looks like that. And then, of course, if you take 5 to the x squared, that's really going to go up steep. So it might look like that, but the key thing is that you have two intersection points there.
Right.
All right. I'm going to make a suggestion, William.
Okay.
Since we have sessions every night this week and your test is on Friday, if you take a few minutes before each session and figure out, maybe circle problems that you want to go over in advance,
Okay.
probably would work out to your benefit.
Okay.
Rather than figuring out the problems in real time.
Right.
For one thing, you can't give it as much thought in real time as you can in advance, picking out the problems that you want to go over.
Okay.
Okay?
Okay. So it says in problems, yada yada, the function f is 1 to 1.
Okay?
Find the inverse of each function. Find the domain and range of f and inverse of f.
Okay?
And so the first one is f of x equals 3 over x to the power of 1/3.
Okay? Now, the very first thing I do to figure out inverses is to turn f of x into y. I don't know that that's absolutely necessary, but it's kind of helpful.
Right.
And then switch the variables and solve for y. That's how you find inverses. It's as simple as that. Switch the variables. So now I got x equals 3 over y to the 1/3. And now solve that for y and you'll have the inverse. Well, how do I solve that for y?
Divide by, or multiply by y to the power of 1/3.
Okay, that's a good start. Then what?
Divide by x. So you get y to the power of 1/3 equals 3 over x. And then, is there such thing as a 1/3 root?
Well, the way we get y all by itself is to cube both sides of the equation. And notice that when you cube the left side, you multiply the exponents together, so you end up with y. Right side becomes 27 over x cubed. There is your inverse function. So I can now say that f inverse of x equals 27 over x cubed.
Okay.
Now, it wanted to know about domain and range, right, of both f and inverse f?
Yes.
Well, let's look at f. What's the domain of f of x? Remember, always be thinking, what can x not be? Can it be negative?
Yes.
Can it be positive?
Yes.
Can it be 0?
No.
That's the only thing it can't be. So
Okay.
the domain is all reals except x cannot be 0. One way to write the domain. Now let's look at f inverse of x. What's the domain?
The same.
Exactly. And that isn't always going to be the same. In other words, the inverse function will not always have the same domain as the original function.
Okay.
Okay, just for your information, it doesn't always work out that way.
Okay.
Well, yeah. Haven't had trig yet, so I can't use that as an example. Well, I kind of can. I don't want to spend a lot of time on this, but if you took the sine function, notice that's not one-to-one.
Right.
So if we are to take an inverse, you can only take inverses of one-to-one functions.
Okay.
So the way they take the inverse of the sine function is to restrict the domain from there to there. And between those 2 points, you'll notice the curve is one-to-one, which is
Right.
to say that it passes the vertical line test and it passes the horizontal line test. But only in that range right there. So when you talk about the inverse sine, you can only talk about this function if you have restricted the regular function. Because otherwise, if I don't restrict the top function, I don't have an inverse. My inverse is not a function. The key thing about inverses is they have to be functions. In other words, after you come up with the inverse, it's got to pass the vertical line test. And it will as long as the original function was one-to-one. In other words, if the original function passes the vertical line test, it's a function. If it passes the horizontal line test, it's a one-to-one function. And if it's one-to-one, it will have an inverse that will be a function. In other words, the inverse of this function looks something like this. I haven't drawn it very good, but you can see that that's still a function. In fact, here, let me draw it a little bit easier. The other thing we know about inverses is that they are reflections about the line y equal x.
Right.
So let me draw the line y equal x, and then I will draw this curve reflected about that line. Something like that. So that's the inverse. That's y equal inverse sine of x. Now some inverses can be a little tricky to figure out. Let me give you one. The inverse of that. What's the first step when you try to figure out inverses?
Switch the x's and y's.
Okay, so that gives us this. Now I got to solve for y. How can I solve for y?
Take the natural log of both sides.
Perfect. That leaves y over there, right?
Right.
So y equal natural log of x, these two are inverses of one another.
Okay.
And this can be quite confusing. This was pretty confusing to me the first time I ran across it. And the reason is that if I wanted to write the exponential expression of that function, what would it be? Not the inverse, but the exponential expression.
Of which one?
This one right here.
Isn't that already the exponential?
No, it's not. That's why it's confusing. I'm sorry. What's the logarithmic expression? I apologize. Sometimes my mind's thinking one thing and my mouth's saying another.
Natural log of y equals x.
Yeah, natural log of y equals x. Notice that is not the same as the inverse at all.
That is a little confusing.
That's y equal natural log of x. This is x equal natural log of y.
Okay.
So it's very important to distinguish. In other words, every exponential expression has an equivalent logarithmic expression, but also every exponential expression has an inverse that involves a log.
Right.
If I were to graph e to the x, it looks like that. If I graph its inverse, it looks like that. Well, that's a perfect reflection over the line y equal x, which all inverses are. And it doesn't matter whether you're talking calculus, logs, or algebra. All inverses are reflections about the line y equal x.
Okay.
Okay? What else?
So this one, it says find the inverse of the function and determine whether the inverse represents a function.
Okay?
But it just gives a list of points. So
Okay.
it gives 1, 2, 3, 5, 5, 8, and 6, 10.
Okay, notice that's not a function, but just a list of points that turn into a function. In other
Right.
words, if I graph that, the first point comes at about there, second point comes at about there, third point comes at maybe there, and the fourth point comes at maybe there. So if I connect the dots, it looks very much like an exponential function.
Yeah.
But it's just a bunch of dots at this point. It's not a continuous function. It's still a function. In other words, as long as you don't have two values of y for a given x, it's a function. And we only have one value of y for every given x. Okay? So if I want the inverse of this function, in other words, if I want to reflect those series of dots about that line, what happens? Well, this dot becomes there, this dot becomes there, this dot becomes there, and this dot becomes about there. And when you reflect dots or xy coordinates about the line y equal x, they merely switch. In other words,
Right.
a point that is 1, 2 now becomes 2, 1. And this point that's 3, 5 becomes 5, 3. All you do when you find the inverse is the x and y values switch. The domains and ranges switch also.
Okay.
So whatever, if I have a function and it has a certain domain and range, and I find the inverse of that function, well, the domain and ranges are going to swap also. Now, we didn't see it on the very first problem we did because the domain was all x's except 0. So when you swap that, turns out to be the same thing.
Okay.
Okay. So I don't know, does that help you on this problem? They should have given you some multiple choices that look like my black numbers below the red line.
Yeah, that does help. Thank you. No, there weren't any options. It just said find the inverse function.
Okay, well, The key thing when you're finding the inverse function is swap the x's and y's.
Right. Hence the doing so algebraically.
Well, it's the algebraic technique we use, and it's also a technique that we use when we don't have the function, but we just have a series of points. Each of these points has an x and a y coordinate. So the inverse of these points is swapping the x and the y. So this 1, 2 becomes 2, 1. And the 3, 5 becomes 5, 3. And notice that if I were to graph these, they appear to be reflections about the line y equal x. Again, as all inverse functions will. Just for your information, when you get to calculus, 2 main branches of calculus: differentiation and integration. Well, guess what? That is the inverse of that.
Okay.
A precise, exact inverse.
Okay. Okay, so I have a quick question. When you're expanding a complicated single logarithm, so for example, something like natural log of 5x over 4 times the quantity of x minus 1. When you expand that, it would be natural log of 5x minus natural log of 4 minus natural log of x minus 1?
Yes.
Okay. Even though the 4 and the x minus 1 are both in the denominator?
Yeah. Let me write it a slightly different way to make it a little bit more understandable. Notice now that both denominators are being added.
Right.
Because there's multiplication going on.
Okay.
And when I remove the parentheses, I get 2 negative signs. Like that. In other words, negative sign has to be distributed to both terms. And that's why you end up with subtraction, subtraction. I don't know that you necessarily have to think about it in this way. You were fine in the way you did it.
Okay.
And you wouldn't necessarily have to do it exactly like this. In other words, you also could have said natural log of 5 plus the natural log of x, right? In place of that. Because you do have multiplication going on in the numerator also.
Right.
So there's various answers. I could have this answer minus, go ahead and distribute the 4 so that you end up with 4x minus 4. That's one answer. Another answer would be natural log of 5 plus natural log of x. That takes care of the numerator. Minus natural log of 4 minus natural log of x minus 1. That takes care of the denominator.
Okay.
These are the same. All 3 of those are the same.
So, because addition and subtraction are commutative, would natural log
subtraction is not. A minus B is not equal to B minus A.
But couldn't you just make it a plus a negative number and then it would be commutative? or commutative, I don't remember the word.
Well, I'm not sure if you mean the associative property or the commutative. The commutative applies to addition. A plus B is equal to B plus A, but not subtraction. A minus B is not equal to B minus A. It does happen to be equal to the negative of B minus A.
But isn't A minus B equal to negative B plus A?
No. Do the algebra. A minus B. So you're saying it's equal to negative B plus A? Well, if I just
Not
keep that.
not in parentheses, just negative B
Ah,
plus.
yes, it is.
Okay.
Yes, sorry. Yes, if I don't have any parentheses, then I can, the commutative property does hold, yes.
Okay. So would saying the natural log of 5, is that equal to negative natural log of 1/5?
Yes, it is,
Okay.
actually. But here's the reason why. If I said the natural log of 5 to the negative 1,
Oh, right.
that's
Okay.
the same as the natural log of 1/5, right?
Mm-hmm.
But it's also, I can take that negative 1 and put it down in front, so it's the natural log. In other words, that's the same as that's the same as that.
Okay.
So I suppose you could do something with that answer. There's even more answers. In other words, I could take those negative signs and thought I had this thing figured out, but yeah. In other words, these negative signs, I could turn them into positive signs and make that natural log of 1/4. Instead of minus the natural log of 4, I can make it plus the natural log of 4 to the minus 1, which is natural log of 1/4.
Okay.
Okay?
So on that, the first like complex natural log in the top left,
Uh-huh.
if there were an exponent of just say negative 1 outside of all the parentheses,
All right, like that. Okay.
yeah, so would that be equal to negative natural log of 4x minus 1 over 5x
Well,
then?
the very first thing I would do with that negative 1 would be to put it there. In other words, it's now equal to minus the log of what you gave me in the first place.
Okay.
Okay? So you can always take that exponent and put it in front of the log thing, even if it's a negative exponent or a fractional exponent.
Okay. So it says, for the directions, it says express y as a function of x. The constant c is a positive number. So the first one is natural log of y equals natural log of x plus natural log of c.
Okay? So first of all, how do I combine that into one log statement instead of two?
Natural log of x plus c, or x times c.
X times c. Put the c because it's a constant. And if that's equal to that, well, now I can equate arguments. In other words, y has to equal cx. And that's what they wanted you to do, was to express y as a function of x. Now the reason they qualified it and said c had to be positive, well, if c is negative, you can't take the natural log of a negative number.
Right.
So C has to be positive.
Okay.
It's a bit like equating exponents when the base is the same.
Right.
If you
Like
have
the
natural
other
log
one
of
was
something,
20.
natural log of something else, then the arguments are the same. You can
Right.
think of it as dividing both sides by natural log, even though that's not at all what you're doing. But you can certainly think of it like that. In other words, I'm going to divide both sides by ln, and that cancels out the ln and leaves y equal to cx.
That can you divide
No,
by a log?
no, you cannot. In other words, this has no meaning. Without an argument, it has no meaning.
Right.
You've got to have what I call the argument. I'm not sure if that's what your teacher calls it or not, but whatever you're taking the log of is what I call the argument.
Okay.
The other way to kind of think about this, I don't know if that's helpful or not, but if I'm looking at this, it's called exponentiating both sides. In other words, I can let this be my exponent to e, and I can let this be my exponent to e. So I've got e to the natural log of y exponent equals e to the natural log of cx exponent. And e to the natural log of anything is equal to that thing.
Right.
E to the natural log of cx is equal to that thing. So you get to the same spot. But technically, that's what you're doing. When you have the log of one argument equals the log of another, when I say you can set the arguments equal to one another, you're doing this kind of algebra, is you're exponentiating both sides. In other words, this is a little bit of a strange concept. If I have x equals y, well then e to the x has to equal e to the y. In other words, I can place a base under each of those. And it's legitimate mathematically to be able to do that.
Right.
I can place any base I want. I could place 17 to the x has to be equal to 17 to the y.
Okay.
In our example over here, it makes sense to use the base of e, because when you take e to a natural log exponent, these kind of cancel out and you end up with that. All right. You got any other final questions for tonight?
Yeah. One big one.
All right.
So if f of x equals log base a of x, show that f of x plus h minus fx all over h equals log base a of 1 plus h over x to the power of 1 divided by h when h is not equal to 0.
Again, they're just saying that because you cannot divide by 0.
Right.
What you're looking at over here on the left is the definition of first derivative. Get used to that expression. You're going to get it a ton when you get into calculus. Okay? So let's figure out what that is. First of all, what is f of x plus h equal to?
Log base a of x plus h.
Uh-huh. So, if we translate all of this, we get log base a of x plus h minus f of x, which is log base a of just x, right? So on the
Right.
right side of the equation, we have f of x plus h minus f of x. I'm going to put it all over h. And now I can say that these two are equal. In other words, in red, that's equal to this. Now we have to manipulate the right side so that we end up with your answer that I'm going to put a square around, a rectangle. You with me?
Yeah.
Okay. Well, we can certainly combine these two, right? In other words, we have two logs in the numerator. How does that combine?
Multiplication.
Okay, so it's the log, let me do this all in black. It's the log base A of x times x plus h, right?
Right.
All over h. That's the first thing I can do.
Wait, how did you get that?
By multiplying x plus h times x.
But isn't that subtraction?
Ah, thank you. You saved me a whole lot of effort because I was trying to figure out how this ends up being equal to that. It didn't look like it was going to. There. Does that look better?
Yeah. Okay.
Okay. Now, notice what that is. That is 1 plus h over x.
Right.
Okay. So, I now can write it as that. I can write it as log base a of 1 plus h over x, all divided by h. Now all we have to do is figure out how to get that h that's in the denominator up to be an exponent. Well, what if I took that exponent and put it in front?
Ooh.
Now they're the same thing, are they not?
Yes.
Which means that I can take a denominator and separate it out. In other words, what I actually have here in the bottom is 1 over h times the log base a of 1 plus h over x. Okay?
Okay.
As I move the h, which was a denominator, to a multiplying in front of the log. That's
Right.
certainly true. In other words, that is the same as this. And now I can take that 1 over h and move it to the exponent. In other words, you can go both ways. You can either move the exponent down in front, or you can move whatever's in front up to an exponent. So I do end up getting exactly what they said you should get. And again, h can't be 0 because you cannot divide by 0. And regardless of where the h is, if I leave the h as a denominator, it can't be 0. If I take it and make it an exponent, well, it's still 1 over h, so it still can't be 0. So you still have the domain restriction that h cannot be 0.
Okay.
But what you've just done is the first step of differential calculus. this whole x plus h, or f, notice that up until now, everything's always been negative, right? Whenever you have an h involved with an x, it's x minus h, or
Yeah.
y minus k, or x minus h squared if you're looking at vertex format for a quadratic. It's always x minus. But the moment you get to calculus, turns in, now it's plus. And when you see x plus something, you know you're in calculus. If you see x minus stuff, you're always in pre-calc. Kind of the way I think about it. Because there's no pre-calculus expressions that involve an x plus some number, or even a y plus some number. Always minus.
Okay.
But this whole thing of f of x plus h minus f of x, that's the numerator of the definition. In fact, there's an h in the bottom, and the exact definition of derivative is I'm going to take the limit of this as h goes to 0.
Okay.
That is the definition of first derivative. You good to go, William?
Yes. Yeah, thank you very much.
Okay, let me just make sure my calendar reflects. I got you tomorrow at 6.
Yep.
Talk to you then.
Great. Thank you very much. See you tomorrow.
Sure.